Okay, this is section 14.5, the chain rule. Just as in Calc 1, Calc 2, we have a chain rule for three-dimensional derivatives. Very similar concept, a little bit of differences, but the concept overall is the same. So the chain rule is for composite functions. So let's recall that if we had dz, so we're talking about differentials now, it was the partial of x times dx plus the partial of y times dy. Well, if we were simply to go ahead and divide everything here by dt, dividing every term by dt would get us the would get us the chain rule if everything was in terms of another variable. I'll explain that in a second. So what we would get is, so let's say that z is a function of x and y. But x itself is a function of t. And y is also a function of t. What that means is that z is your dependent variable. Okay, z depends upon everything. Depends upon x's and t's and everything else. X and y both depend upon t, but they are independent of z, which makes them intermediate variables. So x and y are what are called intermediate variables, because they depend upon something, but they are also independent to something else. And then t, in this case, is strictly an independent variable. So, if we wanted to find the derivative of z with respect to the independent variable t, it would be the partial of f with respect to x. F in this case, however, is z, so we would say it's the partial of z with respect to x, using partial derivative notation, times the dx over dt. Well, there's only one independent variable, so it is a full derivative of x with respect to t. Plus, then we've got this partial of y, f sub y, which is the partial of z in our case with respect to y, times dy over dt, which is a full derivative of y with respect to t. So the biggest thing is going to be the notation here. These are not terribly difficult problems to do, but keeping the notation straight with the partials and the full derivatives, that's going to be the trick. And I will hopefully give you a way to think about it so that it makes sense. The one thing you're going to want to make sure you do is label your variables every single time. So example 1. Use the chain rule to find dz dt. So you notice that that's a full derivative, dz dt, if z is defined as sine of x cosine of y, and x is defined as pi t, y is defined as square root of t. So what you should be able to see, this is very much like the first one, z is our dependent variable. X and y, in this case, x and y are intermediate variables because they're in between. So z depends upon x and y, but x and y depend upon t. So t is your independent variable. So it might be a good idea to go ahead and write your formula out. If I'm going to take the derivative of z with respect to t, it's a full derivative of z with respect to t, meaning every partial that has to do with t has to be included in the chain rule. So I'm going to have to take a partial of x with partial of z with respect to x times chain rule, because x depends upon t, the full derivative of x with respect to t. Notice the difference in the d's there. But z is also dependent upon y, which is also dependent upon t. So it's a partial of z, because it's the other part of z, which is the partial of z with respect to y, times, and y is only dependent upon one variable, so it is a full derivative of y with respect to t. The good news is you don't have to change variables here. What do I mean by that? Well, dz over dt is going to be the partial of z with respect to x. This is z, so the partial of z with respect to x is going to be cosine x cosine y. Remember, we treat the cosine y part like it's a constant. That's the partial of z with respect to x. The partial of x with respect to t, well, here's x. The partial of that with respect to t is just going to be pi. Okay, that one worked out nicely. Plus, partial of z now with respect to y. So now we treat the sine of x like it's a constant. So it's going to be, the derivative of cosine y is going to be negative sine y. So we'll get negative sine x sine y times the full derivative of y with respect to t. The derivative of y with respect to t is going to be 1/2 t to the negative 1/2, or 1 over 2 root t. That's not a minus sign, that's a times. So this is what I mean. You don't have to change the x's and y's into terms of t in this case. If you want to be completely proper about it, you can. So the full derivative with respect to t would be, let's see, cosine of x, which is pi t, cosine of pi t, times cosine of y, cosine of root t, times pi. We could have put the pi out front, no big deal there, minus sine of pi t, because that was x, sine of square root of t, because that was y, times 1 over 2 root t. This stage right here is actually okay. The one below it is just putting everything into terms of t. Okay, either way is perfectly acceptable, whatever way you feel more comfortable with, unless, of course, there's something else that you need to do with the problem. That is perfectly acceptable. All right, let's do a couple more examples before we get into some application here. Use the chain rule to find dz dt. Same idea. So in this case, z is dependent. X and y, once again, are intermediate. And t is your independent variable. So if I want to find dz dt, it's going to be the partial of z with respect to x times the full of x with respect to t, plus the partial of z with respect to y times the full of y with respect to t. And again, remember, you do not have to change the variables. That makes things just a little bit easier to deal with. All right, so let's see here. The partial of z with respect to x, so the partial of this thing right here with respect to x, is going to be 2xy plus y squared times dx dt. The derivative of x with respect to t is 4t cubed, plus the derivative of z now with respect to y is x squared plus 2xy, and then times the derivative of y with respect to t is going to be negative 3t squared. Okay, and that's it. Again, you could plug in the t stuff for x and y. It is not necessary. This is perfectly acceptable. Example number 3. Notice the difference here. We are trying to find the partial of z with respect to x and the partial of z with respect to t. And why is that we're looking for that instead of fulls? Well, let's go ahead and list our variables. So we know that z is dependent. Okay, that's pretty obvious. Z depends upon x and y, so those are intermediate. Because x and y both depend upon two new variables, not just one. So s and t are independent. We have two independent variables here. That's why we have to find two partials, because when you have more than one independent variable, you cannot find the full derivative. You have to find it as two separate partial derivatives. So, in this case, everything is going to be in partials. Not impartial, in partial. So dz over ds, partials. And the only reason for that is because you can only find the partial with respect to s. So it's still going to be the partial of z with respect to x, but then I can only take the partial of x with respect to s. Partial of x with respect to s. Since there's two independent variables, I don't want the partial of x with respect to t, and I can't take a full of x with respect to s because x depends upon both s and t, and so does y. So you can't do it that way. Plus the partial of y with respect, partial of z with respect to y times the partial of y, once again, with respect to s, because that's the variable. So you notice there's no t's in this one at all. So the partial of z with respect to x, 2x plus y. Partial of x with respect to s is 1. The partial of z with respect to y is x plus 2y. And the partial of y with respect to s is t. So that is the partial of z with respect to s. Now we want the partial of z with respect to t, because we have to do it for the other independent variable. Very similar. Partial of z with respect to x times the partial of x now with respect to t, plus partial of z with respect to y times the partial of y with respect to t. And if you really think about it, while you're really not doing this, that partial times that partial would really cancel out, so you'd get dz over dt in both cases. It's not really what we're doing, but it does kind of help to think about how this is going to work out. Okay, so let's go ahead and figure this part out. Partial of z with respect to x, exactly what it was before, 2x plus y. Fortunately, that part doesn't change. Partial of x with respect to t, in this case, is also 1. Partial of z with respect to y, again, doesn't change from the one before. That's always going to happen that way, by the way. It's kind of nice. And then the partial of y with respect to t this time is s. And that's it. So we had to find the two partials because of the fact that we had multiple independent variables. And the easiest way to think about that is however many independent variables are, that's how many partials that you're going to have to solve for if you're trying to get all of it. So the number of independent variables tells you the number of partials that you have to solve for. Okay, a couple more examples, then we'll call it quits on this one, and we'll come back with a second video which deals with more of the application. All right, so again, let's go ahead and list our stuff here. So z, in this case, is our dependent variable. Let's see here. So z is dependent upon r and theta. So r and theta are going to be our intermediate variables. And r and theta are each dependent upon two different variables, s and t. So s and t are our independent variables. So again, that's why we're solving for partials. So let's see. dz over ds. So everything should be ending in s here. So you got to do the partial of z with respect to the first intermediate r times the partial of r with respect to s, plus partial of z with respect to the next intermediate, which is theta, times partial of theta with respect to s. All right, partial of z with respect to theta. That's e to the r, excuse me, with respect to r. E to the r cosine theta. Cosine theta is like the constant, so it's just the derivative of e to the r, which is e to the r. So we get e to the r cosine theta. That's the partial of z with respect to r. Partial of r with respect to s is t. Partial of z with respect to theta. So now it's the derivative of cosine theta, which is negative sine. So it's negative e to the r sine theta. And then the partial of theta with respect to s. So that's going to be a bit of a chain rule there. It's going to be 1/2 s squared plus t squared to the negative 1/2 times the derivative now with respect to s is 2s. All right. And that one's done. Again, you can clean it up a little bit if you want to, but that's finished. I could cancel the 2's out in the last part or whatever. All right. Partial derivative of z now with respect to t is the partial of z with respect to r, partial of r now with respect to t, plus partial of z with respect to theta times partial of theta with respect to t. Partial of z, again, with respect to r, that does not change from the first one. That's always nice. Now the partial of r with respect to t is going to be s. Partial of z with respect to theta, again, same as it was in the first part, times the partial of theta with respect to t. Ironically, it's going to be exactly the same thing, except on the end, instead of a 2s, we're going to have a 2t. Otherwise, it's exactly the same chain there. And that's it. All right, one more example. So we're going to use the chain rule to find the partial derivatives. This time we're going to find the partial derivatives at a specific value. So we want to do it when x and y both equal 1. And we're given r equals the natural log of all that stuff there, where u, v, and w are all functions of x and y. We got a lot of stuff going on here. So what we have is r is our dependent variable. Looks like u, v, and w are intermediate variables. And x and y are independent variables. This one's going to be a little bit lengthy. All right, so let's do the dr dx. Partial of r with respect to x is the partial of r with respect to the first intermediate, which is u, times partial of u with respect to x, plus partial of r with respect to the second intermediate, which is v, times partial of v with respect to x, plus partial of r with respect to the third intermediate, which is w, times partial of w with respect to x. So let's see what we're going to get here. First one, the partial of r with respect to u. It's going to be 1 over all of that stuff times 2u. That sounds right, yeah. So it'll be 1 over all that stuff times 2u, so it's 2u over u squared plus v squared plus w squared times du dx, which is going to be 1, plus partial of r with respect to v. Ironically, it's going to be exactly the same thing as with respect to u, except it'll be a 2v on top. Okay, hopefully you're able to follow that. And then dv dx is going to be 2. And the last one is the partial of r with respect to w. Again, exactly the same thing as the first two, except this time it'll be a 2w on top because that's the derivative of the w part on the inside. And then the derivative of w with respect to x is 2y. All right, so in order to go ahead and evaluate this, because I want to evaluate this when x equals y equals 1, I can do it in multiple ways. I can either figure out what the u, v, and w values are, which is probably going to be easier here, and plug those in, or I can actually plug all the x, y's, and x's and y's and stuff in for u, v, and w and do it that way. I think I'm just going to figure out what u, v, and w are based upon the fact that x and y is 1. So since x and y are 1, if I plug both of those in, then that means my u value is going to be 1 plus 2, which is 3. V is going to be 2 minus 1, which is 1. And W is going to be 2 times 1 times 1, so W is 2. So then we're going to go ahead and plug all this stuff in. So let's see. First of all, all the denominators, that should be easy to figure out. So U squared is 9, V squared is 1, so 9 and 1 is 10, plus 2 squared is 4. So we're going to get 14 in the denominator of all of these. Which is nice because now we're going to do everything in terms of 14ths. So let's see, what's the first one going to be? 2 times u is 6, times the 1 is still 6. 2v is going to be 2 times 1 is 2, but then I have to multiply by this 2 right here also, so I'm going to get a 4. And then 2w, which is 4, times 2y, 2 more is 8. So ultimately we are going to get 18 over 14, which reduces to, what is it, 9/7? Yeah, 9/7. Okay, again, not terribly difficult, but not extremely hard. I mean, not extreme. I mean, you just got to be careful. That's all I'm trying to say. All right, I am going to leave the dr, dy to you guys to do. So I'm going to come back with a second video, and we are going to do applications.